Welcome back. So in this lecture, I'll discuss how to do simulations for robot kinematics, statics and dynamics using MATLAB block diagram based environment, which is commonly known as MATLAB Simulink environment. In this lecture, I'll let you know how to prepare the robot model. I'll introduce you to MATLAB simulation environment and various toolboxes which are required to do such simulation. I'll discuss how to introduce links, joints, sensors and actuators to the joints so that you can actuate the joints using torque, using motion, right? And you can sense for the joint angles, joint torques, okay? So I'll introduce you to all those blocks. I'll let you know how to introduce such blocks and run the simulator on a two-link manipulator. I'll introduce how to use robot Jacobian and how to validate Jacobian matrix. This is very important because once you introduce Jacobian, it should be validated that it is giving you correct values for that. Okay, so I'll introduce you to that. I'll introduce you to gravity compensation block and I'll test that on a two-link manipulator as well. So these are the following MATLAB prerequisites that you need to have before you do such simulation. You need to have environment which is known as MATLAB Simulink environment apart from MATLAB standard basic coding environment. You need to have toolboxes like robotics system toolbox that I'll be using, and I'll be using Simscape or multi-body simulation toolbox that is traditionally being used to do robot simulation as well. Okay, so let us continue. So when you start MATLAB, you could see an environment which looks like this. Okay, so here you see a block which is where you see it is written Simulinks. You need to press that so that you get the Simulink environment here. Okay, from there you just need to create a model. Okay, you can do this. Okay, immediately you will get a blank space where you also see library browser here. So using that, you can see you have multiple toolboxes which are installed in MATLAB. They are visible out here. Okay, so this is the Simscape environment where you see you have a multi-body toolbox which is here, where you have multiple joints, different types of joints. They can be just dragged and dropped to this environment blank space so that you can create the system out here using the joints, using the links. So you have body elements which are here, you have constraints which are here, you have curves and surfaces. So here comes the bearing joint that I have just dragged in here. You can have brick solid, you can have cylindrical solid, you can have different types of other blocks which are here. Okay, variable mass, flexible bodies. So all the blocks are here, they can be dragged directly from here, or you can directly double click here and you can search for a particular block. Let's say it is gravity compensation or gravity torque block. Okay, that can directly be created over here without actually browsing it from the left panel. You can directly get it from here. Okay, so there are multiple ways to insert a block and create a block diagram based simulation here. Okay, so this is the environment. These are the toolboxes that I'll be using, and then you also have a robotic system toolbox that you see here. It's a manipulator algorithms which are here, that includes forward dynamics, get Jacobian, get transformation, gravity torque. So gravity torque that I inserted directly by pressing double click and searching it out here. I could have directly dragged it from here and I'll get exactly the similar kind of block. Okay, so both are same that I need to use here. So you see both are exactly the same. So in order to connect two blocks, you just can put it somewhere here and just click it, it connects. Okay, you can create a circuit diagram of various things, various interconnections based on certain logic here. Okay, so this is your environment. Okay, so there are two major block diagram based toolbox that I will be using. First is Simscape multi-body and second one is robotic system toolbox, where there are multiple utilities and algorithms and robotic system toolbox, where you have manipulator algorithms that contains most of the things that I will be requiring for my simulation. Let us continue, start doing something now. So here I go. So this is the model that I am creating here. Okay, this is the blank space. I have first introduced the block which is called as world frame here. Okay. Second block that I am inserting here is mechanism configuration. Okay, I am setting the parameter here, that is the direction of G here. Because this is mechanism configuration, all the components which are related to configuration of the environment are here. Okay, so it has gravity component as well. So if you remember your two link manipulator, it looked like this. Okay, so you see you have x axis along this, y axis like this, and you have link 1 that is shown in violet color, and you have dark yellow color that is link 2. Okay, this is the manipulator that I am going to simulate. So you see along negative of y direction you should have G. Okay, so this is how the G direction, that is acceleration due to gravity, is directed downward here, and x is along positive direction along this way. Okay, so this is how it is, and z is perpendicular to this plane. We need not to bother here because it is a planar robot. Okay, so here I go. So yes, so what I will do, I will just put my gravity component in an array form. Okay, it's a 0 minus 9.80665 and 0. That means along x you have acceleration due to gravity, that is 0, along y it is minus 9.8, and along z it is again 0. Okay, so this is the configuration that I have done. Okay, the world frame, basically the first block that I inserted, it basically tells you where is your 0 0 0 placed. Okay, so that block is shown here. Okay, so now I am connecting both the blocks, they will use each other. Okay, this is solver configuration. This is kind of integrator that this simulation environment is going to use. By default it is ODE45 here. Okay, now I will introduce the first revolute joint. So that is the first joint which is attached to the ground. Okay, I will connect it to the ground here. Second one is a rigid body transformation, which takes it from the joint 1, okay, to the end of the link 1. Okay, so this virtually creates the frames. Okay, so this joint is the location of the frame. Okay, that is the frame 1 that is attached at the end of the link 1. Okay, and I have renamed it as J1, that is joint 1. This is T01. So method is Cartesian and offset is 1 0 0, that is along x. So you know all the distances along the link length is measured along x. So it is 1 0 0, that means link length will be 1 meter. The unit is set as meter over here. Okay, now I will place the cylindrical solid block. Okay, radius is negligible, I have set it as 0.01. Inertia parameter, I will set it as 1 kg per meter cube. So that is basically the density of the cylindrical block that I have placed. This is going to become your link. Okay, so based on the volume it will create the mass. If it is mass is evenly distributed, it automatically comes at the centroid of that geometry. Okay, color, so as to distinguish between different links, I have put it as 0.800. That means it is 0 to 1 scale for R, for G and B. If it is 0.800, 8 for R and 0 for green and blue components. So it becomes almost like red. Okay. Now I have shown the port where I will be connecting. So this is the frame that I am going to place. So I will put it based on geometry at the end of the link. So I have selected the surface here. Okay. And that direction I have set it as plus x axis along that direction. Okay. You know, link length should be along x axis. So primary axis will be plus x. Okay. Okay. So this is your link and I'll connect it to the joint 1. Okay. Now this is just one link that is first made, and I have created a weld joint and I have fixed another frame which is a blank frame of radius 0.05 mm. It is almost negligible, just to create the frame at the tip of the link 1. I am introducing this. This can be your gripper as well. Okay. I have set this as 0 density so that it should not have any mass. Whatever is the mass, it will come directly at the link only. Rotated it, connected it. So this is a one link system here. Okay. So this is my diagram. So update diagram is done. That can be done directly from the icon which is there, or you can right click and update diagram the way I have done it here. Okay. So this is panning. You can zoom by simply selecting the icon, or you can pan by selecting the icon, or you can use mouse buttons, mouse center button, and drag it or scroll it so as to zoom in and zoom out. Okay. So this is the view I have selected. This is how it looked like. Okay. If I run this simulation, it should swing like a pendulum, isn't it? Because there is a 0 torque that is by default, which is there at the joint. So it swings like a pendulum because there is acceleration due to gravity which was acting downward. Okay. Now I will extend this to 2 link manipulator. You can change the solver here also. There are various ways to do the solution, that is forward dynamic simulation, that is done by integrating the dynamic equation of motion. Okay. Now I will put this at the end. I will introduce a second joint here and name it as J2. This is my second joint. So I will specify position target. So you can insert position at the joints, or you can specify torque at the joint also. Actuation methods can be different. Okay, it can be actuation using torque, or it can be actuated using motion. Okay, so other will be automatically calculated. State target is basically the starting point of the joint. Okay, so that is set as 0. A similar transformation has to go here so as to take it to the tip of the link 2. Okay, so this becomes T01 and then this becomes T12. This is joint 2. Similar cylindrical solid, I will insert it here. I will rename it as link 2. Earlier it was link 1, now it is link 2. Copy and paste. So you can simply copy paste, or you can insert a new block altogether and rename it. Again, offset will be 2 from the Cartesian frame. Okay. So this makes the link length of 2 meter for the second link. Length is 2 meter. graphic, color effect. So this time it is blue color I want, so 0, 0, 0.8. So that becomes blue almost. Now if I run this, it becomes a 2-link pendulum, and it simply swings because no torque is applied at the joint and it was torque actuated. Okay. Now this is a function. What I am going to do now that you are ready with your whole of the system of 2R manipulator with 2 joints and 2 links of 1 meter and 2 meter links. So now you are ready to do anything. So let us start doing inverse kinematics based motion here. Okay, if you remember your old inverse kinematics equation, same I am going to put it here. Just keep watching. I am just inserting the equations in MATLAB programming language here. This is a MATLAB function block. This function can take in end effector position and give you the joint angles. Okay, what I am going to do here, I will insert a trajectory at the end. Okay, let us say I want to have a circular trajectory for the tip of the 2-link manipulator. Okay, so those positions I will keep on pushing to the inverse kinematics function, and in turn it will give me the joint angles. Okay, so if I feed that joint angle to the joints, so it will start moving, the end effector will start moving in a circular trajectory that is planned. Okay, so let us now start coding it. So exactly the same what you can see here is being put here. So right hand, you can see the 2-link inverse kinematic solution by equation 1 and 2. So what I am doing here, I am setting r is equal to 0.3, that is radius of the circular trajectory as 0.3. Okay, total time as 5. X0, Y0 is the center of the circle. It should be within the workspace for the entire planned trajectory. It should not go beyond the 2-link arm reach. Okay, so I remember it was 1 meter and 2 meter for the link lengths for the first link and the second link. So total distance, total circle should not go beyond that reach, that is 3 meter overall from the 0, 0 frame. Okay, so x0, y0 is 1.5, 0.5, link length 1 is 1 meter, link length 2 is 2 meter, x is equal to x0 plus r cos theta. Theta will be calculated based on 2 pi t by total time. T is the instantaneous time, t is the total time. So for one complete total time, it should make one full revolution from 0 to 2 pi. Similarly, y is equal to y0 plus r sin theta, that is basic equation of parametric equation of a circle. Okay, now I am putting in the inverse kinematic solution that is there in equation 2. So this is cosine of theta 2 is being put here. Exactly equation number 2 is coded here in MATLAB programming language. Okay, this is cos theta 2, and sin theta 2 can be calculated based on sin theta is equal to square root of 1 minus cos square theta. So that is what is put here. Done. If you know cosine and sin A, you use 8 and 2 solution to calculate the theta 2. Your solution should not be ambiguous. So for that reason, cos theta 2 and sin theta 2 is calculated exactly using this method. Cos theta through the formula, sin is directly using the cosine. Okay, and theta 1 is as per equation number 1. So once this is coded, you are done with theta 2 and theta 1, you have to return these angles directly on th parameter which is defined here. So, th is a vector that will have theta 1 and theta 2. So, that is stored now at the variable th. So, time can be taken from the clock. Okay. This block takes the input from clock block. Okay. Now, th I will just do demux. Demux is basically it will separate out the two variables which is stored within the th variable. So, it is just to demux that. Okay, it will. So, first variable will get into the joint 1. So, joint 1 will take motion input provided by the input and calculate the torque automatically. Similarly, joint 2 will take motion input and torque will be calculated automatically. Now, you need to convert the values which is available from the Simulink block. So, inverse kinematics block after demux it gives values in Simulink data format that has to be converted to PS data format, that is physical system, because whole of this is a multi-body system, the data formats are different. So, there is a converter which converts Simulink data format to physical system data format. So, joint angle basically once it comes out of this th, it has to go like this. Okay. So, what I have done here, filter input, derivatives are also calculated. Okay. And second order filtering is done. So, this contains both the joint rates as well as the joint angles. So, both are calculated and they are fed to the physical system block, that is joint 1. Okay. Similarly, for the joint 2, okay, joint angle 1, joint angle 2, after being calculated from the inverse kinematics block, it goes to the joint angles. Okay. Now, I will run this simulation. You see it is making a circle in its workspace. Okay, I will pan it, I will bring it to the center. It is run very smoothly and it never goes out of the boundaries. Okay, that is to be decided beforehand only. So, now I will do some modification to this inverse kinematics function. I will increase the radius of this circle now and see what happens. I will run it once again, and in this case it makes a bigger circle in the workspace. Again it is not going out of the boundary now. Okay. Those checks I haven't put here. All the kinematic solution do exist within the workspace. Okay. Checks for that can also be put in the inverse kinematics programming block. Okay. MATLAB function block. You see, I keep on changing the parameters for the circle and it operates with that. The circle center location can be changed, link length can be changed. So, link length you cannot change. You see, if you have to change it, you have to change it in the both the locations, that is A1 and A2 variable here as well as in the blocks. Okay, that is the link length block, everything needs to be changed. Okay. So, now let us use the gravity compensation block. Okay. We have already done it using algorithms that we have developed earlier in the statics one of the lectures. So, again I will use toLink as a variable, import the Simulink model here to create the object for it. Okay, it is toLink planar, this for lecture 3.slx, and it will create an object here in the workspace. You see it is created. Okay. So I will use the block gravity torque. Okay, it uses rigid body tree name as tooling. Okay, that is put here. Okay, gravity direction you have to put exactly the same which is there in configuration. This is the constant that I am putting here, that gives you the range minus pi by 2 minus pi by 2. That is the configuration, initial configuration where you want to keep it stationary. Value here minus pi by 2 provided by the input. Torque is provided by the input. Torque is provided by the input again. These are the joint configuration, and motion is calculated automatically. So joint torque, again I will split them to both the joints, use the Simulink to PS converter, physical system data converter. Simulink to PS converter, that goes to both the blocks now. Okay, now I will run this simulation. So angles are minus pi by 2 and minus pi by 2. So you see, for this particular pose, it is continuously calculating the joint torque, and it is fed to the robot joints. So exactly that much of torque is available at the joint, and it makes the robot at that particular pose as a stationary robot. So it becomes a stationary robot. It is not moving because torque is not varying, and it is controlled by the torque. So torque was sent as an input and motion was calculated automatically. That was set at the joint only. So when you feed in this gravity torque to the joints for this particular angle, minus pi by 2 and minus pi by 2 for joint angle 1 and angle 2 respectively, it makes this robot in this particular pose. Okay. Now I will change the joint angles. So I will make it as minus pi by 3 and minus pi by 6. Same is to be set here also. So minus pi by 3, that is the state target. I have set it as minus pi by 3, and you can notice here torque is provided by the input and motion is calculated automatically. Okay, same for joint 2. For joint 2 it is pi by 6, minus pi by 6. Now you run it again and you see it is a new position that is taken up by the robot. So it remains in that particular position exactly with those two angles. So it started over there, and you are continuously feeding with that joint torque corresponding to that particular angle from the gravity block, and it takes in that torque and robot doesn't move at all. Okay. You can try changing the joint angle once again. This time I am putting it as minus pi by 2 and 0. Same should be put here as an initial state, minus pi by 2, and for the second joint it is 0. Make it go once again and it remains like this. Got it? You can try changing this multiple times and you can validate based on your hand calculation also. Minus 3 pi by 4 and minus pi by 6. You run it, so it goes to a different position now. Okay, so this is how you can keep doing this, and you can validate your gravity compensation block. So maybe you can take some positive value also so as to confirm your exact formulation. So this time I am taking it positive value also, pi by 2 and pi by 2 for joint angle 1 and 2, pi by 2, and this one is pi by 2. Once again I will run it. Okay. So this is how this gravity block, basically it can extract the joint torque corresponding to joint angle. Now let us use the Jacobian function block. Okay, again these blocks can be dragged directly from the Simulink library browser, or you can just double click and insert the blocks. So I am using the transform sensor. Why? I want to know the transformation of the end effector frame from the base frame. Okay. This is basically doing the forward kinematics. I am calculating xy position and velocity. Okay. Position can be directly extracted from the end effector frame. Velocity has to be taken from this block. Okay. These two are Simulink data to physical system block that I have used earlier. This time it is otherwise. So you have to convert the physical system data to Simulink data. So this is basically extracting the Vx and Vy, that is the end effector Cartesian velocities along x and along y. Again I will use a mux which will combine them together and put it to one single stream, and I will put a scope here so as to visualize the data which is coming from this block. Okay. I will run it and I will see how it is coming. You see, when the simulation is executing, creating a circle, how the end effector velocities are happening. Okay. So once it is run, I can directly double click on the scope and I can get the velocities. So now what I will do, I will import the system model and create an object out of it. This is required in order to use Jacobian function block. So I will import the robot, and my simulation model for this is ToLink planar, that is for lecture 2.slx. So this is the complete name of the file, and enter it. It creates a object in the workspace. Okay, now I will double click here. I will get the sensing position and velocity from the joint. So I will check the joint angle, position as well as velocity. So if I take joint angle velocities, you need to convert it to again physical system to Simulink data, physical system to Simulink data. So both of them needs to be converted to Simulink data now. Okay. I will pack them together now. Both the joint angle position is packed together as a single vector. Again I will pack the angular velocity, joint angular velocities here, that is simply the joint velocities. So now I have inserted the block called as Jacobian, get Jacobian. It takes in the rigid body tree object that you have created in the workspace. Body here is body 3. This is submatrix. I am extracting the submatrix from the complete Jacobian, because you just have a complete Jacobian, but complete Jacobian has end effector angular velocity as well as the Cartesian velocity component. Because I know I just need the end effector Cartesian velocities, so I am extracting the elements from this. Okay. So range of rows, So index from starting row is 4th and ending row is 5th. So actually total 6 rows are there. So it gives me the Jacobian. If I multiply it with joint rates, so it should give me the end effector rate. So you know that formula directly. So now the scope should give me the end effector velocity. Okay, the body was body 3, that is the final bodies. Now if I run the simulation, okay, once the simulation is complete, I can check the velocities that comes directly using the transformation and using the Jacobian matrix. Okay, both of them are next to next. Here you see both of them are exactly the same. This is how you validate your Jacobian. Everything should be consistent, and you have used the formula here. Which one? Basically it is Jacobian into joint rates gives you the end effector velocity. Okay, I got it using the Jacobian matrix as well as using the direct transformation matrix as well. Okay, both are exactly the same. Okay, so that's all for this lecture. In the next lecture, we'll start doing robot dynamics. Thanks a lot.